Samples 1B through 5B. We're going to talk about metamorphic rocks today. Before I get started talking about metamorphic rocks, I do want to touch on everyone, just so you know about the FAQ section on the official webpage. If there's any questions, you have to submit them through there. I know we've got the Facebook group going, which is great for you guys to collaborate between one another. But any official rule question needs to go through the Macomb webpage, the Macomb SO webpage. So you can put it through the rule clarifications and FAQs. Recently, we had one about anthracite coal. Previously, back when I was a competitor, we had it listed as a sedimentary rock. But now it's classified under the metamorphic rocks. So it is correct on the list. It is metamorphic. Scientists 2 or 3 years ago, maybe 4 years ago, decided that it is metamorphic. So even though we talked about it when we talked about coal under the sedimentary, it is considered metamorphic, and I would expect you to understand that it's metamorphic. So that's one of the recent FAQs that I got through the Macomb SO webpage. Okay, so let me get started on what makes a metamorphic rock. A metamorphic rock is a rock that's been changed. So we had one rock, something happened to it, and it's changed into a different rock. It has different properties. What caused those changes? The cause of those changes is heat and pressure, okay? Or singularly heat or pressure, but oftentimes both. So a metamorphic rock can be formed from essentially any rock that undergoes additional heating and additional pressure can become a metamorphic rock. So that first rock, before the heat, before the pressure, before it was changed, we call that rock the parent rock. That's the nickname for that first rock before it was changed. Parent rock. I have a couple pictures here showing some different ways that we can get metamorphic activity. So up here, the top picture could be just pressure, just the weight of all the other rocks that have stacked up on top could squish those lower layers and change them based on the pressure. There's heat that could change them in both what they call regional metamorphism, which would be a large area having heat, like I guess the bottom part of the top picture. That whole area would be changed by heat. Or they have contact metamorphism. If you have just a little bit of magma that kind of flows through some cracks, all those rocks that are around it, they kind of get cooked or changed. So we call that contact metamorphism. So there's different forces that can happen to change those rocks. There's basically one feature that we look at that separates certain metamorphic rocks from others, and that's whether or not they're foliated. So foliated is a fancy word for if it's got lines that it'll break on, or maybe not break on, but lines that you can see. Okay? Can somebody tell me, is there a sample in your kit that you would say is foliated? Which sample would you say? What's the rock name of it? Gneiss. Gneiss is an excellent example of a rock that's foliated. So it's got those stripes that are oftentimes black and white. But stripes, you can see foliations in it. Is there another one? What do you think? Slate, that's a good one, okay? So gneiss and slate are two excellent examples of rocks that are foliated. Now, non-foliated rocks, we look at them and we don't see any lines, any planes in there that separate anything. So does somebody see one that definitely is not foliated in their kit? Which one? Metaquartzite. That's an excellent example, which, by the way, you may hear me say quartzite instead of metaquartzite sometimes. Those two terms are used sort of interchangeably. It's only been the last 5 or 10 years that the scientists have been calling it metaquartzite, and I'm stuck in my old ways. Okay, so there's another thing that we look at that we call the grade of metamorphism. So this is like how much has this rock been changed? How much heat, how much pressure has the rock undergone? If it's low grade, that means it hasn't changed very much. It hasn't had tons of heat or tons of pressure. And if it's high grade, it's changed significantly. That means that it's like almost nothing like what it was when it started. So particularly for these foliated rocks, low grade, we would start off perhaps with shale, right? That's a sedimentary rock. And give it some more pressure, that would form slate, which they look pretty similar, right? So that's pretty low grade. They still look very close. More pressure, it becomes schist, which definitely doesn't look like the original shale, but it still could get changed more. So that's kind of in the middle, that's moderate. Give that schist even more pressure and particularly more heat, that'll give us gneiss, which looks nothing like it. It starts to almost crystallize out the different minerals. And the last step, this one's not in our kit, and it's a pretty rare one to find, is migmatite, which is essentially remelted. It's almost an igneous rock because it's gotten so heated up and so melted that it became what we call migmatite. So I'm going to get started on the very first metamorphic rock that we have to talk about. It's gneiss, so it should be labeled 1B if I'm correct. And can somebody tell me what color or colors their sample is? What's yours?
Black and white.
Black and white. Does anybody have one that's not black and white? What color is yours?
Little specks of yellow or orange.
Little specks of yellow or orange. Okay, how about yours? Yeah. Gray, you said? Yep, sometimes.
Like gray and white.
Light gray and white. Okay, so it's mostly black and white. Like almost all of you said yours was black and white. Sometimes you'll see some other colors, but for the most part, it's almost always black and white. Would you say that it is foliated? Yes? What actually happens, with the reason these bands form, is when it undergoes so much heat and pressure, which this picture is actually sideways to how it happens, the mineral crystals, which are all mixed up in granite or diorite. Granite or diorite are real common parent rocks for gneiss. The minerals are all mixed up, but as the pressure squishes, it almost lines up each of those minerals so that they kind of get squished straight into different lines, which is why you see the usually black and white stripes in the gneiss. It's gotten quite a bit of pressure. It's a pretty high grade metamorphic rock. Sometimes the bands in it are really wavy. If there was both downward and sideways pressure, these bands kind of crinkle up and become really neat. Sometimes you'll see these used for countertops. They make really interesting looking countertops. It's a really hard rock, so it's used for different carvings and filling and countertops and other things. And it's basically similar minerals to the granite and diorite, because that's oftentimes a parent rock. Does anybody have questions about gneiss? Yes?
You said that it came from a long line of like other rocks.
Yep.
What? And the first rock was shale, I think you said. And then slate. Like what happened? So how long is it like heated underground before it was formed?
Okay, so you asked how long it takes to be heated from, let's say, the shale or granite or any other parent rock to become gneiss. I don't know. The scientists probably have a number that it takes a certain amount of pressure, a certain kilopascal rating, and a certain amount of heat, which I don't know either of those things. But those could happen over any amount of time. It might happen in a pretty short period of time or a longer period of time. But it's more dependent on how much pressure and how much heat was put on the rock. And that goes for all of the metamorphic rocks. Yep. Let me show you. I have, I think, just one piece of gneiss here. So this is a piece of gneiss, and if you look at it from this angle, you can barely see the lines, but when you look at it this way, you can see the lines pretty clear. So it's just black and white, but to separate it from diorite, you can see that there's definitely lines. So you could identify this easily as not diorite because of those foliations, those lines. I have another sample here, which is, it's not quite gneiss and it's not quite schist. It's actually probably somewhere in the middle, but I want to show it to you as well. It's got some foliations and lines in here. Okay, so next we're going to move on to marble. So grab 2B, marble. Can someone tell me what color your marble is? What color is your marble? White. Can somebody tell me if their marble is not white, what color it is? What color is yours? What color? Black. Your marble is black. Okay, could be. How about yours? Okay, brown on the bottom. What's yours? What is it? A little bit of gray. Okay. I'll take one more. Go ahead. Okay. A light gray. So traditionally, most often when we think of marble, we think white. That's the common color to think about. Marble can truly be almost any color depending on what is in it. So, you know, I wouldn't doubt the black. I've definitely seen black marble. But it's oftentimes white or grayish or off-white. The parent rock for marble is limestone. Does anybody remember I had talked about putting acid on limestone and it would fizz? Do you remember me talking about that? Now, because it's made up of the same chemicals, the same minerals, marble does the exact same thing. It actually acts a little bit slower because the minerals are a little more compact. So it doesn't fizz as quickly or as rapidly. It doesn't react as much. But it does the same thing. It's those carbonates that are in the marble that react with acid. If you look at your sample of marble, can you see little tiny crystals in it? Little pieces that kind of flash a little bit of light? Those are like a calcite material crystal. Calcite or aragonite, some kind of carbonate. You can almost always see little crystals. Again, marble is pretty varied. It's not all the same all the time, but oftentimes you can see little crystals in there. So what do we do with marble? Everybody's heard of marble floors, right? You may have been to a fancy hall and they had a marble dance floor, or a marble entryway in a hotel, or maybe you have marble floor in one of your houses. Same with countertops, marble countertops. Now, anybody who has a marble countertop, they're really hard to take care of. The marble itself is very porous compared to granite and all those other igneous and metamorphic rocks we were talking about. So they get dyed really easy. If you spill some spaghetti sauce on there, you'll have a red spot stuck on your marble countertop. But it's really fine-grained quite often, so it's really useful for making carvings. Michelangelo and all those old Renaissance carvers, they loved marble. That was their favorite stuff to do carvings out of. Also, if you look at old cemeteries, a lot of times you'll find tombstones that are made out of marble. And do you notice, can you see on this tombstone, it's almost hard to read some of the stuff. It doesn't look very crisp anymore. Does anybody know why it might be like that? Why? Because of the rain. What about the rain? Anybody? Yeah, what else? Okay, there's one big word I'm looking for. What is it?
It started weathering.
Started weathering. You're right. I'm looking for what kind of rain it is that's messing it up. What is it?
Acid rain.
Acid rain. That's the word I was looking for. So rain is oftentimes slightly acidic. So it tends to react, just like I was talking about when you put acid, it bubbles. over hundreds of years. When you look at these 1 and 2 and 300-year-old tombstones that you can barely read, it's slow action from acid rain. I've even heard many of the monuments in Washington, D.C. are made of marble, and I've heard that underneath the Lincoln Memorial there are stalactites that the acid rain formed from dissolving and then re-solidifying that marble. So we also crush marble up into powder, really fine powder, and we add it to different things. We put it in paper to make it real smooth, put it into toothpaste sometimes, paints, to kind of give it a smooth feeling, because the marble grinds up to be very soft and smooth. Does anyone have any questions about marble? All right, let me show you. I've only brought one sample of marble, and it's kind of unique. This is a unique piece of marble. Most of them don't look like this. It's from a particular formation, or a type of formation they call a skarn, which is where the limestone, the parent rock, is really dirty. It's got a lot of other stuff in there. And when it becomes marble, other minerals form inside the marble. So this has little crystals in it, which are not marble. They're actually sapphire crystals or corundum crystals. So that's pretty rare. You don't usually find that. Generally, the marble is pretty much the same all the way through. All right, let me move on to quartzite. So grab sample 3B. Can somebody tell me what the parent rock is for quartzite? What's the parent rock? Sandstone, that's right, because sandstone is almost always made out of quartz sand, right? So, and it's usually pretty pure. So if we put enough pressure onto quartzite, onto sandstone, it becomes quartzite. It's considered relatively low grade. You know, I would say it's low to middle grade. And it basically was from that original sandstone. Now sandstone, we saw some pieces that were grayish and greenish, right? Some that were brown, some that were red, tan. Sandstone comes in tons of colors. And it's usually because of other minerals or oxides or chemicals that are mixed into that sandstone. And those things are carried through into the quartzite when the quartzite is formed. So quartzite you'll find in lots and lots of different colors. It's pretty hard stuff. You know, it's very weather resistant. It's not susceptible to that acid rain that marble is. It's not usually foliated. It's usually pretty consistent throughout. We use it for some building things. It's pretty hard stuff. So it's oftentimes not used for large construction, but sometimes countertops and other things like that. Let me show you a few samples of quartzite that I brought. This one is a reddish, brownish color. It's got a little white stripe going through it. And if you look at quartzite, if you look at the very upper level, it almost looks like a little bit of light could go through it. Like it's kind of a little bit translucent, just a little. So that's one thing that helps me sometimes identify quartzite. Also, on the broken faces, sometimes it looks a little bit granular. So almost like the sandstone pieces were just kind of smushed together, but it almost broke on them a little bit. Not always, but sometimes you'll see that. Here's another piece. I would say it's a brownish color. And then here's an interesting one. It's pretty green. It is maybe a little bit foliated. You can see some lines. A little bit. So, does anyone have questions about quartzite? Yes?
Does it always break so that some sides of it are flat?
She asked if it always breaks so that some sides are flat. The samples that I just showed you, at least these two, these really flat sides were cut on a diamond saw. So it wasn't actually found like that. It breaks pretty irregularly. It doesn't usually break in any particular fashion. Any other questions about quartzite? Yeah. I don't think that quartzite can be used as sandpaper. I haven't heard of that use. I don't know. Okay, so next let's talk about schist. The schist that's in your kit is called garnet schist. Why do we call it garnet schist? Does anyone know? Why? Because it has garnets in it, right? That's a pretty good answer. So hopefully, if you look at your sample, it'll have little dots in it. Those are actually small garnet crystals. Now, garnet schist is just one type of schist. There's lots of types of schist. And the fact that there's garnets in the garnet schist tells us a lot. Scientists have done a lot of experiments in the lab where they take a parent rock and they heat it and they put pressure on it microscopically in a tiny little chamber. And they've observed that it's only a certain small range of heat and pressure that creates garnet crystals. So the presence of those garnet crystals in the schist really tells us a lot about what that rock went through. There's lots of other things that we sometimes find inside schist. Sometimes tourmaline. This is actually faceted tourmaline, just like this is faceted garnets. You find tourmaline, you find staurolite. There's a number of minerals. Most often you find nothing. Most often it's just mica or just other minerals that we would call a schist. But there's a number of other things that can form into schist. The schist usually comes from like a basalt or a shale, something dark quite often, not always. A lot of different things can form through, can become a schist. So it's always foliated though. You'll always see those lines, those planes somewhere in there. It might be real squiggly, it might be pretty flat, but you'll definitely see some planes in the schist. Does anybody have questions about schist? Let me show you a couple samples I brought. So this one, the mica, is very silvery. It's got maybe a little bit of brown color to it, but it's very shiny. It's really reflective and metallic. And the garnets are pretty small, but there's quite a few of them. You can see it's well foliated. This one, the background, the body of the schist is a greenish color, and it's got fewer garnets, but they're bigger. You can see not only is it foliated in this plane, but it's kind of curly and curvy, which oftentimes happens. All right, so next we're going to talk about slate. What's the parent rock of slate? Yeah. Shale, that's right. So slate and shale look really similar, and they're hard to tell apart. They're hard for me, they're hard for you. It's hard for a lot of people to tell the two apart. It's pretty low-grade metamorphic, right? Because it hasn't changed all that much from the shale. I can give you a few tips on telling the difference. One, the slate is going to be harder. It's hard to describe this, but it's a harder feel to it. Two, I'm not asking you to do this with my samples all the time, but if you drop them on a table or on a solid surface, the shale makes a little bit more of a thud, and the slate makes a little bit more of a ting. It's got a little bit of a different sound to it. All right, now hopefully you've all heard that. So slate itself is a little bit, it's moderately weather resistant, I would say. Not extremely, but definitely more weather resistant than the shale, than that parent rock. So it's somewhat weather resistant. But one thing that you know, it always is going to break into flat sheets. Now, traditionally, when we think of slate, we think black. Okay, black is the traditional most common color for slate. Does anybody have a sample that they would say is not black? And if it's not, tell me what color it is. Yeah, what color is yours? Yours has white lines. That could be a mineral, another mineral that seeped in there and was deposited on there, perhaps. Well, how about yours? A little bit brownish, okay, and how about yours? Light gray, okay, how about yours? Dark gray. Okay, so most of yours were some variation close to black. You can see the pictures I have here. Some are greenish, sometimes reddish, sometimes grayish, but it's often black or dark gray. So most of the time, that's the color that you'll want to be looking for. So what do we do with slate? Long time ago, probably more than 100 years ago for the most part, very expensive homes used to have roofs made out of slate. So they would actually cut pieces of slate and nail them onto the roof. It is extremely expensive, both to do that and to have a roof strong enough to hold all that rock up on top of your roof. You have to build the house even stronger than normal. So it's not really done much anymore, but that's historically one use for slate. Another is pool tables. There's sometimes one, sometimes two, sometimes three pieces of slate underneath your pool table. They use it because it's very sturdy and flat. It's always going to stay very, very flat. If it was made out of any kind of wood or anything, it would warp a little bit. And if it was made out of, let's say, granite, it would have a little bit of grain to it that could make, maybe little bumps or little holes, divots. But the slate is extremely smooth. A long time ago, blackboards used to be made out of slate. Now, do they even use blackboards in your school with chalk? Or no? No, they used to when I was a kid. And even then, they didn't use slate for them. But long time ago, they used to. Countertops, both for your house and for chemistry labs. Slate is particularly chemically inert, which means that you can spill a bunch of stuff in chemistry class on that countertop and you're not going to mess it up. It's really neutral, so it's a great material to use for countertops, and they still do use it for countertops in chemistry labs. They sometimes use a synthetic material. It's actually, I think, made out of similar minerals, but it is absolutely used for that. And the last thing I'm going to touch on, even though we talked most about it during our sedimentary, is anthracite. So I do want you to acknowledge that it is a metamorphic rock, right? And the parent rocks are one of these other grades of coal that we had talked about. And it's black and shiny. We pretty much did most of the talk when we talked about sedimentary and the whole coal family. But I do want you to understand that it's considered a metamorphic rock. Okay, we're going to move on to talking about mineral properties. So if you could grab out your A samples, all the ones that are A's, and your egg carton as well. Okay, so before I get started specifically talking about minerals, I want to highlight the difference between a rock and a mineral. Everything we've been talking about up until now was a rock. What makes a mineral different than a rock? Can someone tell me what the difference is? What's the difference? Say it again. That's pretty close. Somebody else Say that one more time. It's completely the same thing. So the mineral is completely the same, right? Whereas a rock is made up of multiple minerals, the mineral is one thing. It's one thing throughout. So a mineral is a pure, right? So that means the same all throughout. Naturally occurring. So that means something that you found outside that formed naturally. Crystalline. So inside, it doesn't have to have a crystal shape that you can see, but inside, chemically, there is a chemically crystalline structure, and it has to be a solid, so it can't be a liquid or a gas. We are going to talk about as many of these as we can today, these properties for minerals that I want you to understand. So color, streak, luster, hardness, density, the crystal shape, cleavage, fracture, fluorescence, and reaction to acid. So first, to talk about colors. Some minerals, the color is extremely useful in identifying it. So, for instance, galena, your sample of galena, every piece of galena you find is going to be silvery or grayish. All of them. But other times, other minerals could be any color. So, for instance, calcite or quartz have tons and tons of different colors that they could be. So the color doesn't help you very much in identifying what mineral it belongs to. So where does the color come from? Usually the color comes from, particularly when it's a varied color possibility, comes from some chemical impurity that's in there, which is something that when you get into middle school and high school we'll talk more about. So color, sometimes very helpful, sometimes not so helpful. Streak. A couple people asked me what that square thing is that was in your box, that white square thing. That's a porcelain tile, so it's an unglazed porcelain tile, similar to what's in your bathroom, except it doesn't have the shiny glaze put on it. And we call that a streak plate. What we do with it is we rub minerals on there, and it powders just a little bit of the mineral. It grinds down the mineral just a little bit, and it leaves a little bit of powder on the plate. And then you can see what color the powder is from the mineral. So the powder, it's surprising with a few minerals that it's not the color that you would necessarily expect looking at. Oftentimes it is, but sometimes it's not. So sometimes it becomes particularly helpful in identifying minerals. Particularly hematite versus magnetite. They look pretty similar, but they have different color streaks. It's really good for the metallic minerals. It's the best. Most of the other ones are often white. All right, luster. So the luster is defined as how the light reflects off of the surface of that mineral. So it's like how shiny it is might be kind of a good term. So you could range from metallic. Can somebody tell me something that looks metallic, either a mineral or something in the real world? Yeah. Galena, that's an excellent example. So galena is definitely metallic. Another one is submetallic, which means it looks like a metal, but it's not really as metallic as being metallic. So it's almost metallic, but not quite. It's submetallic, almost metallic. There's vitreous or glassy, so that means really shiny or glassy. Can somebody tell me one that you might call vitreous? Which one? Pyrite. I would call pyrite metallic. What would you say? Something that's vitreous or glassy. Biotite, it could be. It could be a little vitreous on the outside. But what do you think? Quartz. I would say most of the quartzes are glassy. Your crystal quartz, citrine, amethyst, those are real glassy. Adamantine is a word that's like that vitreous or glassy, but even more. It's extra sparkly, extra shiny. This word is, the root word to that somehow means diamond. I don't know exactly how, but it means really sparkly like a diamond. So sometimes you'll find a sample that looks particularly sparkly, and we'll call that adamantine. Silky. Has everybody felt the fabric silk before? It's a real smooth fabric. It's got a real fine grain. You can see where it was stitched together if you look really close. Can somebody tell me a mineral that looks like you might call it silky? What do you think? Myka. Calcite. Calcite is occasionally silky. The one that I'm particularly looking for is satin spar gypsum. That one's very silky. It almost looks like silk. If you look on that broken edge, looks just like silk. Pearly. Pearly looks like a pearl, right? So kind of dull, but a little bit shiny. It reflects gently off of the surface. Can somebody tell me one that's pearly? What do you think? Feldspar. That's the one I was thinking. Feldspar. That K feldspar, the pink feldspar, definitely looks pearly. The surface is, it's kind of shiny, but not really shiny. It's pearly. Greasy. So greasy is interesting. Sometimes it'll feel greasy. Sometimes it just looks greasy, but it's definitely got a dull look to it. Oftentimes very rounded. Which one looks greasy to you or feels? Anthracite? I would say it's a little shinier. What mineral? Hematite. Hematite sometimes looks greasy. That's one, absolutely. What else? Pyrite. Sometimes. It occasionally looks greasy. There's two that I would say that are oftentimes greasy. That would be halite and graphite are almost always real greasy. They feel, you can even feel it when you rub your fingers on it. It feels funny. So dull or earthy, that means that like no light reflects off of it at all. It looks almost like dried up dirt. Can somebody tell me one that's just not shiny at all? What do you think? Hematite. Hematite is sometimes dull or earthy. That's a good one. Anybody tell me another one? What do you think? Talc. That's a great one. Talc is oftentimes dull or earthy also. Kaolinite is sometimes too. So these lusters, they're not always the same throughout all samples, but there's trends that you see certain ones for certain things. So another thing we're going to talk about is whether they are opaque, translucent, or transparent. So opaque means no light passes through it, right? You can hold it up to the light and you won't see any light coming through it at all. You can't see through it, no light, nothing. On the other end, transparent is something that you can see through almost. So like if you put it down over a piece of paper, you could maybe almost read through it, like a piece of glass. And then in the middle is translucent. So light would definitely pass through it, but you can't really see through it very well. So those are different properties as well. Here we're going to go into a little more detail on a couple of these lusters. There's a couple examples of metallic. We have, looks like hematite and pyrite here. So they're definitely opaque all the time, and they reflect really well. That submetallic, oftentimes a hematite. I think that's sphalerite under there. Not quite metallic, but almost. Adamantine, diamond, right at the very end. Diamonds are really shiny, really sparkly. Sometimes a really sparkly piece of quartz, you could call it adamantine. And vitreous or glassy, both of those words can be used individually, interchangeably, or you could use them together. They mean basically the same thing. And that's something glassy. Oftentimes quartz would be good ones for that. So the next property that we're going to use, this one is particularly helpful for identifying things in the field. I use this a lot when somebody brings me something that I'm stumped with. Both students that bring me things and at work, I'm a jeweler, I occasionally use hardness to test different things. So the hardness is the ability or inability for something to be scratched. So how hard it is to scratch a mineral. there's a number of different ways of rating the hardness. What we're going to deal with is the Mohs scale. It was invented a really long time ago by this guy. His last name was Mohs, right? And what he did was he picked out 10 minerals that almost everyone in the world, every geologist, even home geologist people, might have in their collection. So he picked out things that everybody had that were easy to find, and he gave them a number, rated 1 through 10, based on how hard they are. So they're not exactly the same. Like the distance between a 1 and a 2, and a 2 and a 3, and a 3 and a 4, it's not exactly perfect that it lines up how much different they are. But it's really handy. It works really well. It's a good system for what we need to do. I do want you to know that there's other hardness scales that we're not going to use, but they do exist. There's the Rockwell hardness and a bunch of other things that exist out there. So the Mohs scale. What minerals are on the Mohs scale? Number 1 is the softest, okay? So 1 is the softest, 10 is the hardest. So number 1 is talc. Talc is so soft you should be able to scratch it with your fingernail. If you see up here, your fingernail is about a 2, 1.5, a 2. So you should be able to scratch most pieces of talc with your fingernail. After that is gypsum. Gypsum is the 2 on the Mohs scale. It's very soft too. If you really gouge your fingernail, sometimes you can almost put a mark in it. Calcite is the number 3. Fluorite is the number 4. So far all these are in your kit, right? So that's really handy. Number 5 is not in your kit, I don't think. It's apatite. I'm sorry, yeah, number 5. Number 6 is orthoclase. That would be your K feldspar. Your potassium feldspar is the number 6. Now, as a note up on top here, I wrote steel. If you took like a file or a pocket knife, that's about where it would fall. Is somewhere in that range of a 5. So a file or a pocket knife, some hard piece of steel, will scratch all of these, but it won't scratch these. So number 7, the number 7 is quartz. So whether we look at the citrine or the amethyst or the chert, they're all going to be a hardness of 7, the whole quartz family. Now these ones aren't in your kit. These are traditionally gemstones. Number 8 is topaz. Number 9 is corundum, which is rubies and sapphires. And number 10, this is essentially the hardest natural substance, the diamond, right? So that's the Mohs hardness scale. Does that make sense to everyone, or does anybody have questions about that? Okay. So next we're going to talk about density. This one's kind of hard for me to explain, but I think it's easy for you to understand truly. I'm going to try and explain it scientifically if I can. Ron, you want to interject?
I just have an interjection for everybody to be aware of. It's easy to set up your own Mohs scale so that you can measure things in the field. And to make the Mohs scale work, you need a penny. The penny needs to be from 1980 or earlier, otherwise it won't be here proper. And you get the penny, and then you get a jackknife, which is steel. And if you take the rock that you want to stick and you scratch it with the penny, and it crumbles the rock, so the penny, you put the penny off of their powder, rock powder, then that rock is softer than the penny. And if it doesn't do that, if the rock is harder than the penny, as you pull the penny down the rock, you'll leave a streak of powder on the rock. You know the rock is harder than that. And a jackknife is the same kind of a scenario. You use the jackknife to scrape the rock, and if it leaves powder, then you know that the rock is softer than the jackknife. And if it leaves a silver streak, which would be the jackknife itself is wearing out, then the rock is harder than the streak of the jackknife blade. And now to give you some meaning to this,
Thank you, Ron. All right, so on to density. Density is the relationship between the weight of an item and the volume of an item. So can somebody tell me what the volume is? What's the volume mean, that word? What is it? Yep, length times height times width. So volume means how big something is, right? So a particular volume might be a 2-liter container. The volume of that is 2 liters. Volume is how big something is. Now the weight that we look at is how much it weighs when you throw it on the scale. So when the metric system was invented, they did it very smart. They made water, because everybody has water, everybody uses water. They made exactly 1 square centimeter of water. So you took 1 little centimeter of water, the weight that weighs is 1 gram. So 1 gram is exactly the same, is 1 square centimeter of water. So if we tried to figure out the density of water, we would say that the density is 1 gram per milliliter, because 1 centimeter by 1 centimeter by 1 centimeter is 1 milliliter. So the density of water is 1. So if we had a density number that was higher than 1, and we dropped it in a glass of water, would you expect it to sink or float? If the density was higher than 1 gram per milliliter. Yeah, it would sink, that's right. And conversely, if it was lower than 1, it would float on water, right? So here's what we do with minerals. We can take a sample and we use water to help us figure out the volume. So we take a beaker of water, we measure how much is in there, and then we add the rock in there, the specimen, and we see how much that water level went up. So that tells us what the volume is of that particular sample. So this sample was 20 milliliters. It displaced 20 milliliters of water. Then we took it and put it on a scale, and it weighed 155.8 grams. So doing the math, grams per milliliter, we took 155.8 divided by 20. I'm not going to expect you to do this math, but I want you to understand where these numbers come from. So that number came out to 7.79, which no math is ever perfect, especially in the lab. But to try and help identify this sample, I looked at my chart to see what had a density close to 7.79. And the closest one was galena. Galena is 7.5 grams per cubic centimeter, or milliliter. So, and sure enough, this sample was galena. So everybody grab your sample of galena and grab a sample of quartz, any of the quartzes. Can you feel how much heavier that galena is than the quartz? They're about the same size, right? So weight, since they're about the same size, we can judge that the galena is a lot more dense because it's heavier than the quartz is. But weight doesn't matter, right? We could have a tiny piece of galena and a big piece of quartz, and the big piece of quartz would be heavier. But if we're looking at two that are exactly the same size, the heavier one has a higher density. So density is one term. Another term for density is specific gravity. Those are words that I want you to be aware of. Next, we're going to talk about crystal shape. So these are some shapes that I want you to familiarize yourself with. The first one is cubic. Pretty smart. Sounds like a cube, right? And it pretty much is. So the corners are always right angles in cubic. They're not always perfect squares on the side, but when you look at the corners, they're always 90 degrees. They're always those perfect right angles. A couple of examples that you might see cubic crystals are galena and pyrite. In fact, I would bet your sample of galena probably looks cubic. Next, rhombohedral. So rhombohedral means each face is a rhombus. So there's 4 faces, and none of them, there's no right angles, no 90-degree angles involved. Calcite breaks into these rhombohedrons, or has rhombohedral shape. Monoclinic and triclinic, they're kind of hard to tell apart, particularly because the minerals that oftentimes are monoclinic or triclinic don't form really easy to see crystals. So I'm not going to ever ask you to identify the difference between the two of them. But know that there's either no right angles or a few right angles and some parallelograms on the faces. You'll often see this shape in gypsum and feldspar. And the last crystal shape I'm going to talk about here is hexagonal. So what's a hexagon? How many sides does a hexagon have? 6, right? So if you count around a hexagonal crystal, it should have 6 faces or 6 sides. Quartz and mica are excellent examples. Now, nature doesn't do anything perfect every time, right? So there's going to be samples that either don't look exactly the way they're supposed to, or you've got to look hard to see exactly what it's showing. So keep that in mind. Now, these are some other shapes that I want you to have heard and be aware of. This top one is called a dog tooth. So that means that from the base to the tip of the crystal, it just kind of goes straight, or maybe a little curved, but it doesn't have any parallel sides on it. It's all curved or straight to the tip. Does anybody know by chance what that mineral is in the dog tooth picture? What do you think? Nope. That one is calcite. Calcite comes in a lot of cool shapes, but oftentimes one of them is dog tooth. I'm going to go to the other one on the top over here. Nail head shape. So a nail head shape, it'll have 3 faces that meet to a point, and then a relatively parallel side. So parallel sides, and then 3 faces on the top that meet up. And it's shaped kind of like a nail, right? So we call it a nail head. That piece is actually also calcite. So that's another shape that calcite can form in. This one here is called a fishtail. I think we can all guess why it's called a fishtail, right? Looks like a fish's tail. So this is gypsum. That's a shape that it often forms in. This one's tabular. And the word tabular, we get that from tablet. You think of like a tablet, like a little pill, or a mint is a tablet. And that means that all the sides on the crystal are relatively equal, more or less. Doesn't have to be exact. But nothing is extremely long or extremely skinny. And they're more or less tablet shaped. Here we have an octahedron. What's the root word in this octa mean? What do you think? 8, right? So there's 8 faces in this octahedron. So if we count, there's 1 face right here. 1, 2, 3, 4. And then the exact same thing on the other side. So there's 8 of these triangular shapes. We often find fluorite shaped like this. There's some other minerals that form these octahedrons as well. The last one I want to talk about is a rose, which almost looks like petals of a flower, little blades that are intersected into something that's roughly round shaped. We call that a rose shape. That piece is selenite or gypsum. Oftentimes you'll find barite in a rose as well. Next we're going to talk about cleavage. Cleavage is the way that a mineral breaks when it breaks because of the chemical bonds, because of the crystal structure that's in there. So it's the opposite of what I'm going to talk about in a minute, which is fracture, which is when a mineral breaks just anywhere. So some minerals break in these really predictable ways. So this top one I have over here is it's called basal cleavage. Does anybody see a sample in your kit that you would say has basal cleavage? Which sample? Myka. Yeah, any of the micas very well could have basal cleavage. And that's only one direction, right? The mica, it only breaks into these parallel layers. So we call that one direction of cleavage. Sometimes you'll get 2 directions of cleavage. So there will be a top and a bottom and sides, but there won't be anything particular on these sides. Feldspars oftentimes have 2 directions of cleavage. There's 3 directions of cleavage sometimes, which could be a number of minerals, 2 of which, halite and calcite, both have 3 directions of cleavage. So they have a top and bottom, which is 1 direction, these sides here, which is a 2nd direction, and then the other sides, which is the 3rd direction. The angle that they intersect tells us different things. So halite forms in those squares, those blocks, 90 degrees. But calcite forms into those rhombohedrons, those parallelograms, or rhombuses, I should say. So the angles that those planes intersect tells us about it. So here's some pictures. The basal cleavage, that's a piece of muscovite. Any mica is going to break like that, almost always. These octahedrons, you oftentimes see fluorite break like this. It's a very common way for fluorite to break. Sometimes you don't get all 8 sides. You might only see just the triangular shape, and the rest of it will be broken off. But you should be able to recognize these 3, this basic angle and shape. That's a really good identifier. Cubic cleavage, there's a few minerals that we deal with that break into cubes. Particularly galena and halite are real easy ones to identify. And then rhombohedral cleavage would be calcite. That's one of the easiest ways to identify calcite. If you see a funky crystal, like I showed you the dog tooth or the nail head, a lot of times if you flip it over and look at the bottom, you'll see those rhombohedrons where it broke. And that's one of the easiest tips to identify calcite. Next, we're going to talk about fracture. So fracture is where it breaks when it's not on those mineral lines. So it could break in a number of different ways. One of them is splintery. Can somebody tell me a mineral that looks like it might be kind of splintery? What is it? Satin spar. That's an excellent example of a splintery fracture. Earthy. Earthy. Can somebody tell me one that looks earthy? What do you think? Kaolinite. Excellent. Yeah. So it definitely has an earthy fracture. It's also an earthy luster, right? Hackley. Hackley means really rough and jagged. We call it Hackley. What breaks into a Hackley shape? Copper. Copper does, yeah. Conchoidal. We talked about conchoidal fracture when we talked about a rock, if you guys remember. Can somebody tell me a mineral or a rock that might have a conchoidal fracture? Yeah. Obsidian, absolutely. So that's a rock. We don't usually talk about the fractures as much with rocks, but it shows a really good conchoidal fracture. The quartz family does conchoidal fracture. A few others do as well. And then everything else that kind of just breaks rough, we call it uneven. If you can't really see any pattern that it did or any shape, we call it an uneven fracture. And there's a lot of samples that have uneven fractures. Next, we're going to talk about fluorescence. Richard Brzezowski, the guy that I was telling you about that used to do this when I was a kid, this was his favorite thing. He loved fluorescent minerals. Fluorescent minerals are really cool. What fluorescence is when a mineral will glow under an ultraviolet light. To give you an example that you may have seen, have you ever gone to the bowling alley when they have cool, what do they call it? With cosmic bowling, that's the word. Cosmic bowling, and they put the black lights on and all stuff glows all over the place, right? That property is natural in some minerals. So some minerals will glow under a black light. Ultraviolet light is the same as a black light, more or less. So some minerals will naturally glow under that black light, which is amazing. And oftentimes the color isn't at all like the color looks like under daylight. It's a completely different color. Now fluorescence, the beginning part, fluor, it's named after fluorite, the mineral fluorite. Essentially all fluorite is fluorescent. Like 95% of it will glow under ultraviolet light. There's a number of other things that do too. So this is an example here. This under regular daylight, these are calcite rhombohedrons. And then under the black light, they glow. And look at that. They look the same under daylight, and one glows blue and one glows red. Richard would have been able to tell you what chemical is in the two of them. I'm not sure. But either way, certain chemicals tend to be in some minerals that make them glow. Lastly, we're going to talk about reaction to acid. So we've already talked about this with the limestone and with the marble. It's from the carbonates, right? We talked about that word over and over again, carbonates. So when we put acid onto minerals, onto certain minerals, it will bubble or foam up. And the mineral that does that most often is calcite, okay? All calcite's going to do that. And that's actually the mineral that's in the marble and in the limestone that causes that reaction to acid. So that's all I've got for you today.